Welcome to today's lecture on cyclone separators, an essential device in the world of air pollution control. We'll explore how these systems use centrifugal forces to remove particulates from industrial emissions.
Cyclones are simple, robust, and cost-effective devices. Used as pre-cleaners before baghouses or ESPs, they remove larger particles and reduce dust loading downstream. They operate without moving parts, can withstand high temperatures, and are widely used in cement plants, metallurgical operations, and biomass combustion units.
In cyclones, inertial force is used to separate particles from a gas stream, applied in a spinning gas stream known as centrifugal force. When a particle moves at a constant speed in a circular direction, the velocity vector changes continuously, in direction, although not in magnitude. This creates acceleration resulting from a change in direction of the velocity, which is just as real and just as much an acceleration as that arising from the change in the magnitude of velocity. If a body moves in a circular path with radius r and velocity vc along the path, then it has angular velocity, omega. Thus, the centrifugal force can be written as F equals m omega square r, and this is also equals to mvc square over r. In a cyclone separator, the spinning motion creates a centrifugal force that is more than 100 times stronger than gravity. Because of this, the settling speed due to gravity is so small that we can ignore it. The terminal settling velocity, Vt, that we calculate here refers to the speed at which the particle moves outward, away from the center, which is at a right angle to its circular path. Now, instead of using gravity, we use centrifugal acceleration in our calculation. Also, we ignore the fluid density term. With this, we get the formula for Vt as follows. There are 4 basic steps involved in cyclone operation. Concentration of dust particles along the wall. Under centrifugal forces, when dust particles travel 180 degrees, they move toward the walls of the cyclone. Dust particles thus are concentrated near the walls. Descending vortex. Dust particles of large diameter which are separated along the wall are carried down by the helical stream of gas in the cyclone body and cone. These dust particles are ultimately discharged in the dust bin. The gas reverses its direction and enters the ascending vortex. Dust discharge and hopper flow. The ascending vortex actually starts somewhere in the hopper or dust bin below the cyclone cone. If too much gas is carried into the hopper, collected dust may become entrained and carried up by the ascending vortex. On the other hand, to carry the dust particulates, some gas must be carried into the hopper. Ascending vortex. Somewhere near the dust outlet, the gas from the descending vortex reverses its direction and goes up from the bottom to the top. The length of the ascending vortex is from the dust outlet to the inlet of the gas exhaust duct. This gas may contain particles smaller than the cut size. There are 3 main types of cyclone separators, each with a different way of letting gas enter the unit. Tangential entry cyclones are the most common type. The gas enters from the side, creating a spinning motion inside the cyclone. These are easily recognized and can be seen in many industries, such as wood processing, animal feed production, cement factories, power plants, and smelters. Because they are so widely used, this type will be discussed the most in this chapter. Axial entry cyclones let gas enter straight from the top, along the center line of the cyclone. Inside, vanes, like small blades, force the gas into a spinning vortex. These cyclones are often grouped together in multi-cyclone systems, which generally work more efficiently. The third type is a larger cyclone often placed after wet scrubbers. It removes particles that are trapped in water droplets. In this type, gas enters from the bottom and spins upward. The heavy droplets hit the walls and are separated from the gas. In summary, the design of a cyclone is usually based on how the gas enters and exits, either from the side, tangential, the top, axial, or the bottom sides, peripheral.
The removal efficiency of a cyclone for a given size particle is very dependent on the cyclone dimensions. The efficiency at a given volumetric flow rate is most affected by the cyclone body diameter d. A cyclone consists of a vertical cylindrical body with a dust outlet at the conical bottom. The overall length determines the number of turns of the vortex. The greater the number of turns, the greater the efficiency. The gas enters through a rectangular inlet, normally twice as high as it is wide, arranged tangentially to the circular body of the cyclone. The length and width of the inlet are also important. Since the smaller the inlet, the greater the inlet velocity becomes. A greater inlet velocity gives greater efficiency, but also increases the pressure drop. Many different types of cyclones have been designed by merely varying the dimensions, which are given relative to the body diameter d or d0. Extensive work has been done to determine in what manner the relative dimensions of cyclones affect their performance. A number of configurations have been proposed and studied sufficiently to be regarded as standards. You'll find cyclone separators almost everywhere, from cement kilns to ginning factories. They're used for dust collection, product recovery, and even catalyst recycling. Often, they're combined with bag houses or wet scrubbers for multi-stage filtration systems. To wrap up, cyclone separators are critical tools in industrial air pollution control. They use centrifugal force to separate particulate matter efficiently and economically. While they're best for larger particles, they play a vital role in staged filtration systems. That's all for today. Thanks for watching, and we'll see you in the next module.